Let us start today's external talk. Today our speaker will be Yilun. He is a fourth-year graduate student at MIT EECS. Previously, he has done a research fellowship at OpenAI and a research internship at FAIR, DeepMind, and Google Brain. He is supported by NSF Graduate Fellowship and was a finalist for Qualcomm and Open Philanthropy Fellowships. So, Yilun, please start.
Yeah, great. Thank you. So today I'll present some of our recent work on implicit learning with energy-based models. And if you have any questions or anything, feel free to raise a hand or just ask. So the motivation of the work I'm presenting is the idea that a lot of these, a lot of machine learning systems, for example, object detection, works super well when you have a test distribution that's very similar to your trained distribution. But when you actually try to apply these models in real life, where you're like, let's say you're a robotic system and you're embodied, so you're moving around in the environment, you find that these systems perform a lot worse. For example, it seems to think that this pot is a skateboard, and then this bigger pot is a cup, and then that this table is a car. So what makes embodied learning very different than the typical machine learning applications we consider? So one big thing is if you want to apply machine learning to embodied environments, you need to continuously learn and integrate past experiences together. So if you're a robot in a household environment, as you explore the household, you should learn and gather information from all the experiences that you have found in the house. Another big difference between learning in the embodied setting versus learning on train and test distributions is that oftentimes the environment will change a lot. And you will need to rapidly be able to adapt to new things that you haven't seen before, such as external constraints. Maybe the path that you normally take is now blocked by some object. Another issue is that you need to operate in settings in which the training and test distribution are substantially different. Just because the world is always changing, just because maybe objects are always on the table at one point in time, does not mean that they will always be on the same table in future points in time. And there are also many other challenges that I won't really talk about as much, but for example, if you're an embodied agent, you have to take in all types of multimodal inputs. You have to be able to learn with very limited data, and your world is irreversible. So you have to be very safe and conservative with your actions. So what I'll talk about is how using energy-based models as a way to implicitly learn data and capture the structure in data gives us some useful tools for the embodied learning setting. The first thing I'll talk about is how they provide a natural manner to compose different models together to incrementally learn from experiences. Then I'll talk a bit about how they really allow you to adapt to different behaviors or adapt to different obstacles that you've seen, such as a lamp or some object you haven't seen before, by just incorporating test time constraints into the model. And then finally, I'll talk about how we can deal with train and test distribution shift by leveraging more computational power to adapt the model to harder problems or different problems that you see at test time. So first, I'll give a brief introduction on what energy-based models are and what they symbolize, and then I'll talk about each of these 3 bullets that I talked about earlier. So first up, let me talk about energy optimization. So what do I mean by energy function? What an energy function is that it basically represents some type of concept, let's say smiling. And it takes in some vector of inputs, for example, an image x, and maps it to a single scalar energy, where this energy is very high when your image doesn't match the condition concept that your model is supposed to represent. So in this case, this face is not smiling, so the assigned energy is very high. At the same time, an energy function, when you get an image that does satisfy the concept you want to encode, such as smiling, then it assigns low energy to the image. And so this energy value itself can range from is unbounded, so it can range from -infinity to infinity. But the idea is that the images that are more consistent with the attribute smiling, for example, will be assigned lower energy. And then, so given that you have an energy function, how can you generate or utilize this energy function? The idea is that by taking in some random noise input, you can run lens-driven dynamics, basically gradient descent on the noisy image, to gradually generate an image that matches the attribute that your energy function captures. For example, if you have a smiling energy function, you can generate images that are smiling here on the left. So like what is exactly like mathematically, how does the energy function represent a probability distribution? The way you represent a probability distribution is you basically use that Boltzmann distribution defined by the energy function, e to the negative energy exponential energy is your probability of data points. And then you can run a gradient-based MC procedure called Langevin dynamics, starting from noise, to essentially gradually generate images that exhibit the concept on hand. After our paper in 2019, there was a lot of other works that have worked like gradually significantly improved this type of denoising process using Langevin dynamics. And I think the most popular and well-known ones now are diffusion models. So while diffusion models are typically not known as EBMs, I'll show in this talk that like they're essentially EBMs, and you can use a lot of these operations we've defined for these earlier energy-based models directly on diffusion models. And actually, their functional form is very similar. So if you look at on the left-hand side, what happens is you take a random noise image and you take a gradient descent step on the energy to get a slightly refined image. And with a diffusion model, you basically learn a learned gradient of the energy function. So you have a network that predicts an update to the noisy image. And if you look at this like image formation process, it also starts from noise and gradually constructs your final image. And really, the thing that like allows you to do the exact same things with energy-based models and diffusion models is the idea that both of them formulate generation is this iterative process, which really enables you to, on one hand, adapt your computation for harder problems, as well as compose different models together. So how do you train these energy functions? The way that you typically train them is some type of wake-sleep. So what you do is you try to minimize the energy of real data. And you basically try to maximize the energy of hallucinations. And you basically, to find these hallucinations, you run some type of like gradient descent procedure. So essentially at the beginning, your energy function will be mostly uniform. So all your data has like both data and fake images all have high energy. And then over the course of training, you gradually decrease the energy of real data while increasing the energy of hallucinations. And an alternative way to really train these energy functions is to just follow what people have been doing with diffusion models, where you can also, instead of explicitly training the energy value, you can just train the gradient of the energy function. So you basically can supervise the gradient of each data point, or like the gradient of the energy landscape, by learning how to denoise images. And I'll talk mostly about 3 different applications of these models on images, robot plans, and reasoning. But actually, a lot of these things, these models can be used on a variety of additional settings, for example, proteins, text, 3D shapes, and there's many other domains you could also use them in. Cool. So that ends my introduction on energy functions. If anyone has any questions, feel free to ask them now. Okay, cool. So the first thing I'll talk about in terms of interesting things you can do with energy functions is the idea of compositionality. So imagine that I have there's a question. Yeah. Right. So yeah. So that's a good question. So why does lowering the energy of training examples while increasing the energy everywhere else not cause overfitting? Well, so in practice, these networks have a finite number of parameters. So because there's so much information in the data, it's very hard. The only way you can really accurately fit everything would be to model that underlying generative distribution of data. And one thing to note is that this is not just for energy-based models. I think all likelihood models, autoregressive models, or anything like this, all these models try to maximize the likelihood of data and minimize the likelihood of all other data points. So the main thing is just like parametric encoding efficiency. So because you only have a limited number of parameters to encode like hundreds of thousands of images, the only way you can really encode this is by representing the data distribution. Okay, cool. So going back to the idea of composing different energy concepts together. So imagine that I have one energy function that I've learned, which describes smiling faces. And then at a later point in time, I learned a second energy function, which describes female faces. The interesting thing about using energy functions to capture each of these factors is that if you add these two functions together, you can get a new energy function. And this new energy function is just these energy functions added together. And if you minimize or optimize this energy function, now you are able to generate faces that are both smiling and female in nature. So essentially, by representing different concepts or like factors as energy functions, it gives you a natural way to nest different functions together at test time by simply optimizing the addition of each function. So here's another illustration of this idea. Imagine that like my first energy function I learned at an earlier point in time captures 4 corners of a square. And a second energy function I've learned at a later point in time captures the right half of this square. By adding these two energy functions together, I can generate samples that exactly converge to the combination of these two ideas. So like these 2 points, which are low energy under both of these energy functions. So more formally, let's consider what types of compositions you can do using energy functions. So imagine I have an energy function in blue, E1, and an energy function in orange, E2. The first thing I can do is I can generate images or other data modalities that exhibit factors both in energy function 1 as well as energy function 2. And this is what I described earlier, where you basically just try to minimize this energy function that's the sum of these two energy functions. Alternatively, I can also try to generate samples that are either in energy function 1 or energy function 2. So in the previous example, it would be both female or smiling faces. And the way I can do this is I can essentially add both of these models parameterize a probability distribution. And you can basically sample from the distribution that corresponds to the sum of each individual distribution. And if you do some math, this is approximately equal to this log sum x expression on the energy functions. Another thing you can do is you can try to generate images that have one factor but really do not have another factor. So what you can do is you can negate the first energy function and add it to the second energy function, and this will generate images that exhibit the factor in the second energy function while not having the one in the first one. So you would generate smiling faces that are not female, for example. So here's some examples of what you can do with these operations. So let's say you train 2 individual models, maybe at different points in time, one for smiling and one for male faces. You can use the previous energy operation to generate smiling and male faces, or smiling and not male faces, or smiling and female, or not smiling and male faces. So you can continuously make more complicated expressions or compositions of images by just composing these models more and more. And a similar thing you can do is you can also use these models to represent relations of objects. So you can imagine that a single energy function represents a small red metal cylinder below a small green rubber cube. And then you use the same energy function to represent the second relation, a small red metal cylinder to the right of a large blue rubber cube, and the third expression. So the same energy function, so you condition the first energy function on this text, you condition the second energy function, which has the same weights, but just with different text conditioning with this text, and the third one was this text. And then by simply adding this energy function together, conditioned on each of these different pieces of text, you can generate images that exhibit exactly these set of relations. And then in contrast, you can't really do this with traditional generative models because they're not really composable in nature. So you can't just compose them with respect to each other. And then here's a more visual illustration. So when you have a single relation, you generate an image with that single relation. When you have 2 relations, you generate images with both sets of relations. When you have the 3, you similarly generate images with 3 sets of relations. And the interesting thing about this is that it really allows you to generate scenes with much more sophisticated combinations inputs than what you saw during training time. So at training time, we trained each of these relation models with a single relation, and with scenes, I believe, with 3 objects. And then you can see that you can generate up to 5 objects. So you can both generate more objects as well as generate more complicated scenes by composing these models together, in addition to being able to learn these models at different points in time and then compose them together. So like I said earlier, it turns out that diffusion models are a particular instantiation of energy-based models. So you can apply these operators to diffusion models also. So here, I'm just going to show a couple examples where you can, if you just directly encode a very complicated sentence into the diffusion model, it struggles to although it can generate certain images very well, with much more complicated captions, it's unable to generate each individual aspect accurately. But if you compose multiple different diffusion models together, then you're able to generate all types of different images. And then this is a more low resolution version. Here's a more high resolution version using the more recent stable diffusion model, but the same idea. So you can generate mythical trees and a magical pond while having the background be dark or not dark, black and white or not black and white. So essentially, this shows that this type of this type of composition can be very helpful across different scales of models, and including very large pre-trained ones. So another thing that's interesting about using energy functions to represent different components of images and using them to compose images together is you can also discover them in unsupervised manner for input images. So imagine I have this input image here. How can I decompose it in an unsupervised manner into the underlying factors of variation inside the image? So it turns out that you can see the paper for details, but it turns out with some tricks, you're able to construct a set of 4 energy functions, each of which describes one cube in this scene. And then if you compose these 4 energy functions together, you get the original scene. In a similar way, you can take a face, and you can construct 4 separate energy functions that describe each of the individual aspects of the face. For example, this is the facial features, this is the background, this is the hair color, and this is the skin color. And by combining them together, you can get your original image. And what happens is because these factors are kind of independent, you can use the same types of energy composition operators I talked about earlier to combine and create all types of different images with new factors. And here's an example. So you can take this image here, and if you train this energy function on these images, you'll find that each of the energy functions can decompose the camera position, the lighting direction, and the lighting intensity. And what you can do is you can just take this. You can take the energy function representing camera position, and you can just basically modify that one while you're fixing all the other energy functions for the scene. And then you see that the scene gets re-rendered at different locations. You can similarly fix all the factors except for lighting direction and vary that. And you can see that the lighting in the scene changes. Or you can just fix all the energy functions except for the one representing lighting intensity. And then you can change the underlying lighting intensity in the scene. And then in a similar way, you can actually also discover these energy functions in one data set with maybe just spheres and cylinders, and a second data set which are trucks and pens. And by just adding these these different sets of energy functions together, you can recombine and construct scenes with objects from either data set 1 or 2. Okay, cool. So that was what I wanted to talk about in terms of compositionality. Again, let me know if there are any questions. Yeah, so that's a good question.
I have a question.
Mm-hmm.
Oh, sorry.
No, sure. Go ahead. I can answer the question.
Yeah, I have a question about this composability. So you mentioned that, say, for example, you train 2 energy function and then you try to combine them. Do you need to do another kind of training, or you just take the train model and then just directly apply that?
Yeah, so we directly apply it. So I think this is also answering the other question in text. I think this is a big difference between this and supervised learning. So in supervised learning, if you want to combine 2 models, you need to fine tune them a bit. But in our setting, we just combine them at test time. There's no fine tuning or anything like at all.
I see. Okay.
Okay, cool. Yeah.
Thanks.
Yeah, thanks. And I guess going back to what's the difference between comparison to playing those loss terms in usual supervised learning. Yeah, I think the main idea is these energy functions. They essentially you can imagine that they capture these individual factors that enable you to just directly compose them. So when you have different loss functions, you have to train your network. And with these energy functions, you can imagine they're even learned loss functions. You can just combine them together. There's no fine tuning needed. So you just generate the image without any need for fine tuning. Okay, cool. So the next thing I'll talk about is the idea of adaptability. And this will mostly be talking about the context of robot planning. And the general high-level idea is that you have an energy function, which is essentially a trajectory energy function. And this basically captures what are reasonable trajectories in the world. And then you have a second energy function, which can kind of be your cost function. And it can tell you like, what is your underlying goal? It can tell you like, what reward are you optimizing? Or it can tell you what test time constraints you want to use. And by adding these two energy functions together, you can get a new energy function, E of x, that basically captures both whether trajectories are sensible or not, as well as capturing like whether they satisfy each of these conditioned elements. And by adding these two energy functions together and running a trajectory optimization, which is basically the optimization procedure we were talking about earlier on the image setting, you can synthesize trajectories that have all of these have both of these properties. So here you can see. So here I'm going to visualize the trajectory optimization procedure. So imagine that you have each of these dots are joints of a Majoko robot. So this is a hopper and this is a walker. And at the beginning, basically the points are random. So they're not really in a coherent trajectory. And basically, as you run this trajectory optimization procedure, what you'll see is that you essentially get a consistent trajectory. So like each of these points now are now like connected to each other and form a reasonable trajectory. So you can imagine that whenever this trajectory optimization procedure happens, you basically run optimization on these joints subject to these external cost functions or constraints. So what are some concrete examples of using this? So the first concrete example is the idea of using this previous framework, energy function, as well as these like cost functions to do reinforcement learning. So you can learn one energy function, in this case, a diffusion model that represents different trajectories. And you can learn a second energy function, which is just a value function, and it assigns rewards to each state. And you can imagine that this type of decoupled framework allows you to construct different energy functions for different tasks. So you can train one single large generative trajectory model and just use separate energy functions to specify different behaviors you would like. But anyways, so how does this perform? So by simply just adding two energy functions together, one for the trajectory and one for a value function or not even value function, it's just the sum of the rewards at each state. Just by adding these two functions together, you can see that this approach actually works quite a bit better than most model-based approaches, while also like performing very comparably to some of the best offline reinforcement learning or reinforcement learning approaches. But I think that really the power of this approach is the idea that you can do all types of other flexible behavior synthesis by using this type of energy framework. So what's another interesting one? Another one can be this idea of goal planning. So what you can do is you can have one energy function that's just representing the entire trajectory. And you have a second energy function that basically represents constraints on your trajectory. So this energy function says that the first state of my trajectory must be the start state S, and this final state in the trajectory must be this goal state G. So then when you try to optimize the sum of these two energy functions, all your trajectories always have the start state and this given goal state. So here we illustrate this type of planning procedure. So we essentially train the diffusion model or energy model on all different possible trajectories in these three maze environments. And then at test time, we just specify an additional energy function that says the start state has to be here in the circle, and its goal state must be the star. And then by simply running this optimization procedure, you can now generate much more complicated plans in this environment, where these plans here are actually of length 512. So they're very, very long plans. And if you use some like type of MPC controller, even with ground truth dynamics, you're unable to accurately solve this problem. Yeah, and you can see in this setting here, our approach essentially just significantly outperforms all prior approaches, where this uses a ground truth model, and these are different offline reinforcement learning approaches. And another interesting thing you can do is you can have one energy function represent a trajectory, and you can have a second energy function represent a cost function. Basically, something that describes an aspect of the state you would like to do, you would like to have, and you can add these separate energy functions together. And the idea here is that this is really an analog to trajectory optimization, where like this energy function here is just like the normal cost functions you use in trajectory optimization. But if you do this, well, so first this shows samples from the first energy function. So if you learn an energy function on different trajectories of block stacking, you're able to generate a stack of different blocks. Now, if I add these test time constraints, so I add a constraint that the red block needs to be on top of the blue block, a cost function that specifies the purple block needs to be on top of the red, and a third energy function specifying that the gray block needs to be on top of the purple, you essentially are able to generate these conditional trajectories, which essentially stack the blocks in the particular configuration you would like. Cool. Yeah. So that's the second section. So essentially, another interesting thing you can do in terms of these energy functions is this idea of that adaptability, where you can use the energy functions to specify different behaviors, and you can basically at test time change the behavior subject to external constraints you have. So again, if people have any questions, happy to answer them. How do you not get stuck? Yeah, so that's a great question. So how do you not get stuck in local minima when trying to enforce hard constraints? So one thing that's different in our setting than the traditional trajectory optimization setting is the fact that our model, which is this learned energy function E1 here, it's learned. So it's continuous. There are no discontinuities. While typically when you have hard constraints and a simulated state, if you run optimization, you have all types of local minima. So because this model is learned, you have much smoother optimization landscapes, and this is why you are able to synthesize these behaviors. Yeah. So how scalable is this type of method? Well, so I think in this setting here, this energy function E1 of X, this is just a model representing different trajectory of agents. So this model here, you can just imagine you can train a very, very large model. So like people have been able to train diffusion models on huge amounts of text to image data sets. So it seems like it would be possible to scale these also to millions of trajectories of robots or other agents. So the second energy function here, this basically specifies what you want to do at test time. So although you use different test functions depending on the behavior you want at test time, this is just a very lightweight model. So you can just, for in this case, like if I want to do block stacking, I just specify these 3 blocks that I want to stack. So like this is more of a task specification. So I don't think this is actually, you don't actually really need to train this. Like in this case, this is not trained. This is handcrafted. But you essentially like, these are just, you can imagine these energy functions are essentially ways to bias or like make this large unconditional energy function generate the trajectories you would like. So there's actually not that much learning, and this learning is very cheap.
Yeah, maybe I have a follow-up question on this. So you said this E2 function, you don't need to learn. You can just manually specify.
Yes. Yeah, I should have said this earlier. So this energy function here, which is the energy function of our trajectories we always learn, but this energy function here is manually specified in this case. It's actually also manually specified in this case here. So we just manually specify a start state and a go state. So like as long as you have a differentiable energy function, it doesn't have to be learned. It can be either handcrafted or learned.
Okay. So say for example, like can this one be applied to self-driving, for example? Like, I don't know, like we want to move from A to B, and then you just specify the start position and the end position in the map, and then hopefully this model can just do everything.
Yeah, I think so. Yeah, I think we're pretty excited about this idea of these models generally for long horizon planning, because it seems like you can do like 512 horizon planning pretty effectively. And yeah, you just literally just specify the start state and the go state.
But how do you handle the uncertainty and dynamics in the environment, right? Like I think like some of here like it's heavily all the environment is static. But like in self-driving, you have like, maybe keys running out behind occlusion or whatever, those kind of case.
Yeah. So one thing. Well, so this is a probabilistic model. So it will try to essentially plan one path from the start state to this go state that has some probability of reaching, that like has positive probability of reaching from the start state to go state. But during the course of interaction, if like the environment changes, then you would need to replan, because this plan is not reactive, right? So you just generate a plan from. But you can imagine that as you're running down this, as you're going down this path, at any single point, it will generate a plan that has some probability of succeeding. But if the dynamics in the environment change, you can just replan. So you can just iteratively replan this every time step.
I see. Okay. And also you mentioned that like the E1 function. I think that was like like maybe you have to use some very big network and a lot of data to train.
Mm-hmm.
You also mentioned that like it's doing some optimization. So like the others, I mean, like normally people when people doing like this trajectory optimization stuff, like they use IRQR or some of those MPC server.
Mm-hmm.
And seems like those can maybe having like some guarantee for hard constraints. But can this diffusion model like also have like satisfy the hard constraint, like it never collide with obstacles?
Yeah, well, so it's not guaranteed to satisfy the hard constraints. Well, but if you construct these, cost functions, right, that correspond to these hard constraints, you can check to see if the final trajectory satisfies these hard constraints. In general, we find that with like, if you have enough like loss on the, if you have enough like cost on these constraints, then you are able to usually satisfy them. But yeah, it's not guaranteed because this is a continuous space optimization problem. Your intermediate solutions do not necessarily satisfy the constraints, but typically the final ones do.
Okay, so like if you really want to have like this hard constraint, so you probably still need to run some optimization based method finally to ensure this hard constraints.
Yeah, exactly. Yeah. But you would imagine, this could be a very close solution, and then you would want to run some optimization method.
Okay, I see. Okay, yeah, thanks.
Thanks. Did you compare with transformer-based methods, which also use inpainting? So I think so we compared with a couple offline RL benchmarks. We did not explicitly compare with transformer, but I think that like other people have tried these tried transformers for like infilling. And my understanding is that the diffusion model, like with this type of energy optimization procedure, is a bit better. But yeah, no one has really, I think, tried these Actually, I'm not exactly sure how you would do it with the transformer. I guess you could train the transformer to. You would have to train on any order autoregressive transformer so that you can fill in the densities correctly, so that you can inpaint. So yeah, I guess it might be hard. I don't know. There was not really an obvious transformer-based method you could compare with.
One more question, sorry. Like for this E1 model, does it need to be like fixed length of like how many states you can handle?
No, it does not actually. So we actually talk about this in the paper. I didn't have time to put it in this presentation. But you can, our network is like a bunch of temporal 1D comms. So you can actually generate variable length trajectories with it. So I think in the paper we show that you can generate like, even if you train only on length 100 trajectories, you can generate like 50 or length like 150 or 200.
Okay, well, thanks.
Thanks. Okay, cool. Yeah, so that's the second portion. So the final portion I'll talk about in terms of energy optimization is this idea that you can actually use this energy optimization procedure to do reasoning. So what does that mean? So when I talk about reasoning, I mean like, so like, let's say I have some addition problem, or I have some like matrix multiplication problem. I want to find the final answer for this problem. And the idea is that you can formulate finding the solution of this matrix problem is essentially running this energy optimization procedure, where you have an energy landscape over possible solution Z, and you essentially run this optimization procedure until you get a minimal energy solution. And the big idea here is that when your data distribution changes, like maybe at test time you see a different problem that you haven't seen before, by simply running a more complicated optimization procedure on this new energy function. So it's assuming that your energy function does generalize to this more complicated domain, which it seems like generally, I'll show some experiments where it seems like it does. This iterative computation gives you a way to adapt to distribution shift or mitigate it in some extent. Okay, so going to specifics. Let's consider, for illustrative purposes, the example task of addition. So imagine I have some like vector Rm, which is basically like maybe it has like 200 entries, and I have an additional vector y, which also has 200 entries. And then, so you have a vector x, which is like maybe 200 entries, and a vector y, which is a possible solution, which also maybe has 100 entries. What you do is you learn an energy function that takes in this input x as well as a possible solution y, and it outputs a single scalar value energy, where again the energy is high if the solution's if the energy is high if the solution is incorrect, and energy is low if the solution is correct. So again, inputs x, and then the solution y. Where here these inputs are 20 by 20 matrices. So they're not super informative, but the idea is that each of these values indicate a value in the matrix. And yeah, and like I said earlier, you basically have this energy function for high and low energies. So then how do you get a solution for this addition problem? The idea is a very similar idea to the ones, the two settings I talked about earlier, where you basically can run an energy optimization procedure to find the minimal energy solution to this y. So you can kind of initialize your y to be random noise. And you essentially, as you run optimization, it gradually recovers to a minimal energy solution. And then this solution will ideally be the correct answer to the two inputs. So as a rephrase of what I was talking about earlier, now how can you convert all types of different like algorithmic problems into this iterative reasoning framework? So most algorithms or a large number of tasks you care about, you basically have some inputs and you have an output you would like. And then the idea is that you just formulate the outputs that you would like is an optimization procedure on your energy landscape defined on the inputs. So in this case, if your two inputs are x and y, then you basically run an optimization procedure on z to find your final solution. And so we tried this task, we tried this operation on a variety of different algorithmic reasoning benchmarks. And the first one we try it on is the shortest path computation. So our approach, which is REM, which is on the left, is compared with recurrent network, as well as a bunch of other approaches in the paper I linked. But essentially, you train these models on size 10 graphs. So you basically learn how to compute the shortest path on size 10 graphs. What you do then at test time is you try much, much larger graphs. So you try like size 15, 20, 25, and size 30 graphs. So even though these graphs turned out to be much larger and harder then to solve, what we find is that if you use this energy optimization procedure to get your final solution, you can generalize to these harder task instances by running more computation steps. So with a size 10 graph, which is a size you trained on, it takes like maybe 10 steps of computation to get the right solution. But then with something like a size 30 graph, you can, after running 40 steps of computation, you can directly recover the final answer. In contrast, if you use something like a recurrent network, you'll see that with size 10 graphs, if you run more steps of computation, the solution gradually gets better. But as you test much larger graphs, this recurrent procedure just gets very easily out of distribution, and basically the error gets much, much larger for these larger graphs. So essentially, this type of energy optimization procedure gives you a more natural way to do iterative computation, and this iterative computation is beneficial for larger graphs. And we show very similar results for different settings, such as connected components and copying edges in graphs. And here, this is showing. Here, I'm going to show the actual optimization procedure. So essentially, you have these. You have a start point in green and a goal point in blue, and you basically have different connections between each of these vertices that are basically continuous values. And at the beginning, you start with this random path that's initialized here. And essentially, as you run the course of optimization, you keep on exploring different trajectories until gradually we recover the ground truth one, which is the shortest path. So like as you run optimization on the energy landscape, you gradually go and recover the final path. And then you can do this a very similar thing for matrix addition. So here you have two input matrices that are 20 by 20. Here's your prediction, and here's the error map. And as you run optimization, you see that the prediction gradually corresponds to the sum of these two values, and the error map gradually gets to essentially 0. And actually, what we find is if you use this type of optimization procedure, you can perfectly add very, very large matrices. And if you actually, you can also perfectly multiply matrices if you are able to, like, if you compare the input matrices in log space. But you find very similar trends where, like, using this energy optimization, you can do additional different types of algorithmic tasks like matrix inverse and matrix completion. And another interesting thing about this idea is if since I formulate this like type of computation as an energy optimization procedure, I can actually compose multiple different operations together. So instead of adding 2 matrices together, maybe I want to add 8 matrices together. What I can do is I can add the first 2 matrices, get their output, and then add this output with a second matrix and so forth 8 times. And why is this challenging? Well, this is challenging because as you run these inputs more and more, they get more and more out of distribution and incorrect. So like you only train these models to add numbers, let's say between -1 and 1. And now you have values that could be like between -3 and 3 or like larger. And what you find is with this iterative reasoning, you can accurately compute this regardless of the number of compositions you essentially add. And here's an example. So here we added four matrices. These are just the first 9 entries of 400. And here's the final solutions you get. So they're not perfect, but they're relatively close compared to like the ground truth answers of -1 and -0.32 and so forth. And so essentially, in conclusion, I've basically presented this idea of energy optimization and I've shown some useful applications of it. On one hand, to like compositionality, like you can compose separately trained models together, which can be very helpful if you have to learn at different points in time. I've shown that they can enable very adaptable behavior synthesis, which is useful when you have all types of external constraints or blockers that suddenly occur. And finally, I've shown that they are useful for iterative computation and enable you to like adapt to like different out of distribution inputs and problems that you haven't seen before. Yeah, so at this point, I'm happy to take any questions or anything on any of the previous sections.
First of all, thank you for your talk. It was really nice. Let us close here. Yes, and dear colleagues, if you have any questions, please, you have a chance to ask.
I have 2 questions for your final section. Can you hear me clearly?
Yep, I can hear you clearly.
That might not be good. Yeah, can you be a little bit more specific? What do you mean by optimization? Like like you train this energy function, and then you said like doing optimization. Can you elaborate that a little bit more? And the second question is, I don't know, like you've mentioned that like you try to solve the shortest path, like with like maybe very small graph, and then you can. Seems like this iterative minimization on the energy function can generalize well to like larger graph, while like maybe I think you were trying to compare to some supervised learning methods, right? And those supervised learning methods seems to have like auto distribution problem, which makes sense because it just never train on those large graph. But why does energy-based model can generalize better? I mean, if you never train with those large graph, do you have any insights why?
Yeah, cool.
Yeah, basically two questions. Yeah, thanks.
Yeah, sure. Yeah. So first, let me talk a bit about like this. So what do I mean by this optimization process? So what happens is, so recall that I have this energy function that basically takes in an input and a possible solution, and it outputs a single scalar final energy. So to recover a optimized solution, what I do is you initialize the solution. You initialize the solution to be random noise. So here, And you basically keep on running gradient descent steps on the energy function. So you take this random noise, you run one gradient descent step on the energy function, then you keep running gradient descent steps on the energy function. And you just keep repeating this operation until you've hit an energy minima, which happens after so many number of steps of optimization. So that's what I mean by this energy optimization procedure. So in terms of generalization, or why does this energy function generalize better? So I think one reason why is you can imagine that this energy function is some type of verifier. So essentially it assigns low energy when you have the correct graph, or like a graph with the shortest path. And like it returns and it basically gives you incorrect answer, or like it says this is incorrect when you do not have the shortest path. Well, learning a verifier, so even if you learn a verifier for a size 10 graph, right? You just like you can just check to see like if the shortest path between two things satisfies like this like kind of like Bauman-like update, where you just see is like if you do a dynamic programming update on the shortest path, is it maintained or not? So there's a very easy operation that you can learn to verify that you have recovered the shortest path. So because this operation is much easier to learn, let's say, than explicitly generating the final solution, the final shortest path solution, you can imagine that maybe this operation itself generalizes much better to larger graphs than like explicitly generating the output. And I think so in more general cases, I think that like this overall, it feels to me that like this verifying operation, or like just checking if your solution is correct or not, this is a function, this is like a learning problem that I think is easier to generalize for a lot of different problems than just trying to directly predict the outputs. And I guess this is also like seeing like in like P equals MP, or like how like verifying is much easier than like generating the final solution.
I see. Okay. Yeah, thanks. I think that makes sense, like the P and NP kind of arguments, right? Like supervised learning maybe is trying to directly, propose the solution, versus here is like it's just a check on not, doing the check. Okay. So for your optimization kind of like thing, so yeah, like you start with some random noise and you get a bind energy function. Like energy value. How do you compute gradient from that? Like, do you do like longevity gradients, or like those process?
Yeah.
Or...
Yeah, so basically we use Langevin. So you just compute the gradient of the input with respect to the final energy. The only difference is because this is a deterministic prediction problem, I don't add any noise. So you just do the gradient descent step with respect to the energy function.
Okay. And how many iterations do you need to have, like, to reach to some good solutions? And then like would it also have like some latency constraints if you if in some like real-time applications, for example?
Yeah. So this is much. So I in practice need around like 5 to 10 steps of computation. But then like if you have these larger graphs, then you need more, like around 30 or 40. So it is very slow. So yeah, I think that a definite issue is that like in real-time application settings, maybe like this would not be as useful, because like you would have to run this for much longer. I think on the other hand, it's also kind of interesting, because it feels to me like when we as humans enter a new environment that we haven't seen before, we actually think a bit think for a while, and then we make a solution. So like you imagine that this kind of models that behavior. But I agree that on one hand, for like real-time applications, this is not a good. This might not be good.
Okay, cool. Thanks. Yeah, but I think like there's also like like in the diffusion model process, right? There's also seems to be a lot of work on how to speed up the diffusion process. I don't know, like as you said, like EBM and diffusion, maybe they are the same model, and maybe like some of those speed up methods can be also applied here.
Yeah, that's a good point. Yeah, you can also definitely use some of the speed ups in diffusion models. Like I think some of them are using more second order optimizers. Some of them are distilling models. So yeah, I think both would be very helpful for improving performance also.
Cool. Thanks. Yeah, very nice talk. Yeah, very inspiring. Thanks.
Yeah, thanks so much.
Hi, Yilun. Yes, I have also a question about generalization. What do you think? What is the main like key feature of EBM models for generalizing to like unseen inputs and distribution, something like that? Is it, for example, the like some smoothness and continuity in terms of probabilistic landscape? That's why, for example, if we didn't see it, because based on the smoothness, we can still like guess what is the probability here, what is the energy. And yeah, and the second related question here is if we have like really non-connect, for example, if we have some inputs that can be like very close with respect to some metrics, I don't know, LP metrics, or doesn't matter, but still, for example, could have really like different outputs. So, for example, some combinatorial problems or something, can here energy-based models help? Yeah, that's the question.
I see. Yeah. So first question, I guess, in terms of generalization, why do these models generalize? So I think one reason I've always thought that these models seem to have like, why can you do some of these combinatorial generalization, or like why can you like adapt to test time constraints? I've always thought one reason is this idea of like iterative computation, because like if with a lot of neural networks, you just like get the latent, like for example, again, and you just generate the output. And if you do that, it's really hard to compose or like generate outputs that are not the concepts or like the conditions you were given. Because if you have something that you haven't seen before, then like maybe there's not such an easy mapping. But like I think like for each of these applications here, to generate a final solution, you have this iterative process where you basically take one step, gradient descent step was the energy function, and then you refine it, and you basically have this very like iterative procedure, which gives you ability to adapt to mistakes or like out of distributionness. So like maybe you add something, it gets out of distribution, and then this like model kind of like has the opportunity to use iterative computation to refine it a little. So I think that iterative refinement is the reason why you can do a lot of these more like adaptability or like generalization to these composition things. And then similarly on the reasoning setting, I think that when your problem is different, or it's not something you've trained on, maybe having a straightforward mapping will get you out of distribution. But having this iterative computation where you like iteratively update things, that it seems like that gives you some type of feedback and allows you to be a bit more robust to this. So in terms of the second question, what about like, can you train these models on very like combinatorial domains or domains with many constraints? So that is a very hard so in principle, you could like use this energy training procedure where you like sample in this very combinatorial space and try to minimize energy of real data and increase energy of fake data. But like sampling in very high dimensional combinatorial spaces is very hard. And actually also training diffusion models in like, or like using this like more denoising objective to train these energy functions, that's also very hard because it's very highly discrete. I think there are some like so like currently I think both are challenging problems, but I think there are some ways to go and circumvent these. So one thing that people seem to be doing is like you can represent these high dimensional combinatorial spaces as lower dimensional latent spaces, and then these spaces are much more connected and continuous. And then a lot of the sampling or like a lot of the things I'll talk about now I think would work much better.
I see. Thanks. And one maybe follow-up question here about this. Like my first question about this. You said that supposedly this iterative process can be a key here to generalization. So we can get, for example, out of like local minimum or something, for example, to auto distribution, then finally go to the solution. But is it, for example, really the case even if we have not so smooth as on your right picture, like energy landscape, but for example, very, I don't know, spiky things. Can we really do the like efficient TBM sampling even in this case?
Oh, if you have very spiky energy land. Well, I think even if you have very spiky energy landscapes, you could use something like parallel tempering or something like this, right? Like because you have the final output energy of your solution, right? You could like just do optimization with many restarts, and then you can choose the best one. But I guess it's still like it seems like because you can like iteratively rank and get your solutions, you can just choose the best one that you get.
I see. So the combination of parallel tempering and then there's some. Okay, makes sense. Thanks. Yep.
Hey, can I ask a question that's relevant to your other papers?
Yeah.
So I read this one called Improved Contrastive Divergence Training of EBM. So I think I think one major point you mentioned here is that if we only like do the loss term on like positive and negative examples, then it will lead to an adversarial mode. That's why you introduced like the KL, like the so-called KL divergence term, the missing gradient. Could you elaborate more on like what would that adversarial mode be like?
Yeah, sure. So normally in contrastive divergence training, what happens is you try to decrease, so you want to decrease the energy of real data while increasing the energy of fake data. But to generate fake data, you basically try to run kind of this noisy optimization procedure on your energy landscape. So there's kind of this tension where on one hand, your model is trying to make the energy values of your sampler be very high. But at the same time, your sampler is trying to effectively sample from your energy landscape. So if the energy model makes everything you sample high, then it's much harder to sample correctly from the energy landscape. And so that's an actual practical thing that seems to happen when you run EBM training. Is over the course of training, it gets harder and harder to generate negative samples, and then you need to run more and more MCMC steps until you get a correct negative sample. So what the KL term seeks to correct is basically it just encourages the samplers to still be able to get low energy, despite the fact that the energy function is increasing the energy values of the samples.
I see. So if you use like a separate distribution to generate the negative examples, would that alleviate this problem?
Yeah, so that's a good, so using a separate generation, that would definitely significantly help this problem. I think the issue then though is that your generated samples are not necessarily the adversarial modes in your model. So that might lead to some issues, but yeah, that would definitely alleviate this issue.
I see. Thank you.
Thank you.
Maybe I have one practical question. Like, say, for example, if you want to do the task of predicting the goal position, like, say we have a self-driving car at, timestamp t, and we want to, like, it has a ground truth of, the goal position in like t plus 5, right? One way you can do is like you encode the state and you just directly predict the goal position using some supervised methods like regression, for example, just a simple one. And maybe the other one is like maybe you can train a energy EBM model for like to predict the goal. Do you have any suggestions like whether EBM can potentially perform better, or like maybe this simple, supervised learning like directly predict the goal could also work good in this particular problem setting?
Yeah. Okay. So I think that if your goal if your goal has a lot of uncertainty in it, then using the supervised learning won't work so well, because because supervised learning will just like blur all the goals together, and then you won't get an actual real goal. But if you have a lot of multimodality, then learning some type of energy-based model across possible goals I think will definitely be very helpful, because it can capture this multimodality and like get each of these different solutions. In contrast, if given your current state, there's no uncertainty, like the goal is pretty much a deterministic function, like you can always predict it, then I think just using supervised learning would be better, because then you don't really need to model this type of energy landscape or uncertainty at all. You can just L2 is sufficient to predict the final output.
Okay, yeah, thanks.
Yeah, thanks.
I think like for this particular problem, right, like because the future is uncertain, like, say for example, what is a 5 seconds goal position for this vehicle? Yeah, I think there may be a lot of uncertainties, but supervised learning can also, I mean, maybe it can also capture like, some of the uncertainty, right? Like if you're using like mix of Gaussian or like, any of those methods.
Yeah, definitely.
What is the advantage of EBM compared to those type of methods?
Yeah, so I think if you use mixtures of Gaussians, Well, if you use a single Gaussian, it's unimodal, so then you can't really capture multimodal data. If you use mixtures of Gaussians, I guess one question is how many mixtures do you use? Like how many modes does your data actually have? And there's a lot of you can construct all types of densities of possible outputs where it's really hard to model with mixtures of Gaussians. Even in the 2D setting, if you have rings of outputs, it's impossible to capture that with 2D Gaussians. So I feel like in practice, in real life, a lot of the uncertainty distributions we have are not that cannot be that accurately modeled with even with mixtures of Gaussians. So I think that this just gives you a general purpose to model arbitrarily complicated distributions. So in many settings, if the mixture of Gaussians already works very well, then I think you should always run that. But you can imagine that this approach, because it can in principle model any data distribution, it should be able to more flexibly generate solutions that are diverse and capture all the multimodality needed.
So you were saying if mixture of Gaussian kind of model can potentially also work well, and we probably don't need EBM here. So that I'm not sure if I understand correctly what you just said.
So what I was saying is it depends on the problem you have. So I think that if the multimodality in the problem is relatively simple, then it's possible that mixture Gaussians would be able to model it. But if the uncertainty is much more complicated, which I think in many domains it is, then you'll just find that probably this approach will just be more able to sharply capture multimodal distributions. There are a limited number of multiple distributions that mixtures of Gaussians can capture. But these types of learned energy-based approaches can capture arbitrarily complicated probability distributions in principle if there's enough data.
I see. Okay, thanks. Yeah, makes sense.
Yeah, thanks.
Hey, sorry, I have one more question.
Uh-huh.
So about this conditioning or composing for EBM. So I think you mentioned that, for example, if you want a constraint, you could jointly add the energy function together and jointly minimize. So let's say I have some conditioning, for example, in the goal prediction scenario we just mentioned, let's say your EBM distribution is over a set of coordinates, which is your goal position, but your conditioning might be your environment, the scene information.
Right.
So for example, besides just concatenating those features together, or adding the conditioning as a separate energy function, what's your recommendation here?
I see. To basically incorporate this conditional information you've seen, right?
Yeah. Yes.
Yeah. I guess actually the main ones I would try is I guess those were the ones you talked about actually. I would either add it into training, so I would just condition it on the conditioning, or I would just add it as additional energy function. So I guess you can construct an energy function that's matches the compatibility of your current state prediction and the conditioning, and then you can use that gradient. Yeah, I'm actually not sure if there's another way to do that. Were there any ideas you were thinking about in terms of that?
And I was just kind of asking. So about the composing, I was seeing your other example, the castle, generate an image of a castle and with black and white and without black and white. And I would notice that it's not a direct black and grayscale of the colored image. So the content still change a little bit. So do you think that's a result of something that not so disentangled in the energy, or is it because the optimization procedure would lead to a slightly different path?
Yeah, so the optimization procedure is stochastic. So you do get different solutions. But also, I think your first one is also good. I think that there's these models are not entirely disentangled. Black and white and the earlier descriptions, they're not completely disentangled with respect to each other. So I think that also might have some effect.
I see. Thank you.
Thank you.
Colleagues, any other questions?
Sorry, I have one more question. So I think all of your methods would use some kind of gradient descent to get the local minimal energy. But for
Mhm.
example, if your output space is low dimensional, like the XY coordinates, does it make sense to do like an exhaustive query? For example, I just query like 1,000 possible locations and take the argmin of that. So would that hurt like or damage some of the benefits of an EBM model?
Oh no, I think that would be great. Yeah, I think that actually works even better. So if you can just exhaustively sample these data points, the energy landscape, energy value you get is much better, I think. And
I
there's this
see.
paper called implicit behavior cloning, which I believe where they use energy functions to model like policies, and they basically just do this exhaustive search, and it works great for them.
Gotcha. Thank you.
So maybe let's finish for today. Thank you one more time.
Okay, thank you.
Yes, it was a really nice talk. Yes.
Yeah, thanks.
Let's probably let's meet one more time, maybe in person in the future.
Yeah, that would be great. Yeah. Okay, great.
Yeah.
Thank you guys.
Thank
Yeah,
you.
thank you, Yilun. Yeah, hope to see more great work from you.
Thanks.
Thank you.
Thanks.
Bye.